Hello everyone and welcome to the first part of our 28th lecture for MAT353. I appear to have neglected to have placed a date on today's lecture. If I were to do so, I would have dated it as 4/15, and that is actually last Wednesday's date, assuming you're watching this on Tuesday, the 21st day of April. Last Wednesday, if you'll recall, we were supposed to have a lecture, but I postponed it because I wanted to prioritize doing some grading and getting that graded work back to you before our midterm on Friday. And also to make sure that I could make myself available to folks if they had questions leading up to that midterm. I do apologize that grading hadn't been done earlier and that we did have to postpone that lecture. This teaching from home stuff has just been a ton of work. Creating these online lectures has taken a lot longer than I expected, so I'm juggling things as best I can here. That being said, we do still have a lecture that's due for today as well, and I will get that up sometime this evening. So this lecture is meant to cover last Wednesday's time slot, and later today we will have a lecture 29, which corresponds to today's time. And of course, because these are asynchronous, you can fit them in whenever you can. We'll have another lecture Wednesday, tomorrow, and if you wanted, you could push these back and imagine that we had a Thursday lecture this week instead. So, what we're going to be doing today is just practicing triple integrals. So we've thought about three different coordinate systems in 3-space, that is Cartesian, cylindrical, and spherical, and we have thought about computing integrals using each of those coordinate systems. What we're going to do today is more of the metagame of a math class, which is how do you know which technique to use, and it is more like the real-world situation. So it can be a little bit unfortunate sometimes in a math class when you're studying a new technique and then you get to some example problems or sample problems, you know that they're going to use the technique that you just studied. And so you have this contextual clue about what's going to be the most appropriate way to approach an integral, for instance. In the real world, you just encounter integrals and you have to decide which method is going to be best to compute that integral. And that's the kind of problem we're going to look at today. So I'm just going to throw some problems at you, and you'll have to decide how best to proceed. We're going to get to that. I want to start with one particular example that I like because it's an example that we can think about in all three of our in all three of our different coordinate systems and see how it works out in each. So we're going to be talking first about the volume of an ice cream cone. We're going to let E be the region above the half cone, z equal to the square root of x squared plus y squared, and below the sphere of radius square root of 2, given by this expression. And I want you to find for me the volume of E. So my part in this is going to be attempting this problem in Cartesian, and it's not going to work well. You may already guess which coordinate system you would best like to use, and it's probably not Cartesian, or it's hopefully not Cartesian. But we're going to begin by looking at the problem in Cartesian. That'll allow us to think about the geometry and to try to set it up a little bit. And then I will pass the problem off to you and have you actually attempt it in a more appropriate coordinate system. So I'm going to start by thinking about what this region actually looks like. So here is my cone, z equal to the square root of x squared plus y squared. It's the upper half of the cone. We studied cones of this type way back at the beginning of the course when we talked about quadratic surfaces. You can see them in chapter 12 of Stewart. And that cone, that mathematical cone, looks like this ice cream cone. That half of the mathematical cone, the upper half of the mathematical cone, looks like an everyday ice cream cone. And then the sphere of radius root 2 is going to serve as sort of the ice cream top that sticks up above that cone and has a rounded profile to it. And you can see the sphere is going to keep swinging around. If we were to continue it here in some sense, it would continue the sphere. It doesn't come straight down and meet the cone in a vertical line necessarily, but it would continue off in this way if you were to continue it. So the point of that is kind of that there's very little ice cream sticking up above the cone here. But this is what the region looks like. This is what E looks like in 3-space. If we draw it in the xy plane and we project the region down into the xy plane, then we would be looking at something like the shadow that the region casts on the floor, and that would give us a disk of some radius centered at the origin. If I instead think about what this region looks like when projected into the XZ plane, then I would be looking at a vertical cross-section of the cone, and we would get a region that looks like this. So here's my upper half of my cone projected into the XZ plane, and here is the sphere that tops off the region projected into the XZ plane. And again, you can see how the sphere projects into a circle, and how the circle would continue around were we to not restrict it to lie above the cone. So we want the volume of this region E. We're going to use this theorem that tells us that the volume of E is the triple integral of constant integrand 1 across E. We are going to need to describe, well, first let me say, I suppose, that is a theorem from lecture 25 of this course. Just like we can compute area by taking a double integral of 1 across a region, we can compute volume by taking a triple integral of 1 across the corresponding region. And that's what we're going to do here. If we want to be able to compute this triple integral, we need to figure out what our limits of integration should be if we write this triple integral as an iterated integral. And in order to do that, we need to be able to describe our region E in Cartesian coordinates. So that's our next step. We need to figure out what our limits of integration are going to look like, which is to say we need to figure out how to describe this region using Cartesian coordinates. What are our bounds for x, y, and z in Cartesian to describe this region? And let me also note that this is not a problem in Cartesian that I would ask you to do. When we studied triple integrals in rectangular coordinates, I mentioned that there is a type 1, a type 2, and a type 3 region. There are such things as type 1 regions, type 2 regions, and type 3 regions in 3-space in Cartesian, just like there were type 1 and type 2 in 2-space in Cartesian. But we skipped that. It was something that we had to let go for the sake of being able to do justice to the rest of the course, having lost a week's worth of lectures. So I am going to set it up here. That's why I'm doing this part for us, is so that you can just follow along with the setup. It shouldn't be incomprehensible to you. It's not overly esoteric. It should look familiar to some other stuff that we've done. And so hopefully you'll be able to follow along well with how we set up this region in Cartesian. But it's not something I would have asked you to do because we largely skipped this section. We only mentioned that it existed when we went through lecture 25. So we do want to describe this region in Cartesian. When I thought about the projection of the region into the xy plane, I saw that I got a unit disk, or not a unit disk necessarily, but a disk of some radius in the xy plane. The edge, the outer boundary of that disk, is this circle, and I'm going to need to know the radius of that circle, which is to say the radius of the disk, which is the projection of my region into the xy plane. So what's going on with this circle? How do we get this circle that was the projection of our region E into the xy plane? Let's draw E in 3-space again. And in this picture you can see that this circle that we're concerned with now is actually the projection down into the xy plane of the widest portion of our region. And that's exactly this circle here where ice cream meets cone. So right where these two surfaces intersect, that gives us the widest portion of our region. And when that widest portion is projected downward, that gives us the outer boundary of the projection. And so we want to know what this widest region looks like. What is this circle where ice cream meets cone? That's going to be the intersection of the surface that is our cone with the surface that gives us our ice cream top. So this was our upper half of the mathematical cone, and this was the sphere that made the upper boundary of our region. So we want to know what does the intersection of those two surfaces look like. So I'm going to solve both of them for z squared, and I'm going to be able to set those two expressions for z squared equal to each other. If I solve the sphere for z squared, I get 2 minus x squared minus y squared. That's equal to z squared. Z squared is also going to be equal to, if I square both sides of this expression, I'll get z squared equal to x squared plus y squared. So I set the equation for the sphere, given here, equal to the equation for the cone, given here. Well, the equation for z squared on the sphere and the equation for z squared on the cone. Set those two equal to each other, do a bit of algebra, and I come to the expression x squared plus y squared equals to 1. So this circle where ice cream meets cone is in fact a circle of radius 1. And when I project it down into the xy plane, I get the circle of radius 1 centered at the origin in the xy plane. The unit circle centered at the origin. And so our projection into the xy plane is actually the unit disk centered at the origin. And we have a fair amount of experience at this point representing the unit disk in Cartesian coordinates. We'll let x go from -1 to 1, and for each of those x values, we'll let y go from the lower half of the circle, y equal to the opposite of the square root of 1 minus x squared, to the upper half of the circle, y equal to the square root of 1 minus x squared. All right. So this describes the unit disk in the xy plane, and then for each such xy pair in this unit disk, we'll have our z values moving from the lower surface, the cone, to the upper surface, the sphere. And if I do that for each such xy pair in the disk we've just described, that will give me every point in my region E. Every point in E projected downward corresponds to some xy pair in the xy plane. If I take that point in the xy plane, move up, and begin to consider z values at the cone and take all z values between the cone and the upper surface, then I will have all the points in the region. If I do that for every xy pair and every corresponding z, I get all the points in my region E. That is to say, we are going to want to let z go from the cone to z value for the upper portion of the sphere here. So this is z equal to the upper half of the cone, which is our lower surface, and z equal to the upper hemisphere of the associated sphere, which is our upper surface. And now I can set up my triple integral, which gives me volume. Excuse me, folks. I think that has more to do with spicy food I just ate rather than a viral infection. But we are now going to set up our volume as a triple integral of the integrand 1, and we can now express that triple integral as an iterated integral with respect to z, then y, then x. X is going from -1 to 1, y is going from the lower half of the unit circle centered at the origin to the upper half, and z is going from the cone up to the sphere surface. So from our ice cream cone to the top of our ice cream for each of the z values. And this doesn't look terribly natural. Hopefully you have begun to start to get suspicious when you see limits of integration, especially like the ones here for y that look like the lower part of a circle and the upper part of a circle. That should indicate that there are some circular regions. They never look very nice in Cartesian, but might look better in cylindrical or possibly in spherical coordinates. I am able to compute the first antiderivative here with respect to z. That's simple enough as we have a constant integrand. When I take z at the upper limit minus the value of z at the lower limit, I get this difference here of 2 square roots, and then I'm at a loss. Fairly quickly, I have reached a point where I'm not able to proceed in an obvious way. I don't know how to compute this integral. So things got bad quickly. It was worth thinking about it just so we could have a look at the region and think about the geometry, and also at least see how we might set this up as an integral in Cartesian. But I am going to ask you now to re-attempt this problem using a more appropriate coordinate system. So you can back up if you need to, have a look at the setup, the exact equations for the two surfaces, and I'm asking you to find the volume between those two surfaces using whatever means seem best to you. So definitely, especially today, all we're doing today is practicing problems. The point of today is for me to throw problems at you and have you work on them in a way that is similar to what could happen on an exam. So please do actually pause the lecture and give it a shot. It is especially important for today's lecture, as today is simply just a chance to give you more practice. So take advantage of it if you will. Go ahead and pause the video, and we will reconvene in a moment to consider a solution. Alright, so moving forward with this problem, we're going to do it in both cylindrical and in spherical. Both are possible. The limits of integration turn out to be a little bit simpler in spherical, so that's nice. But for a lot of folks, it's difficult to develop the intuition of how to express regions in spherical coordinates. So if this problem makes sense to you, better sense to you in cylindrical, it might be worth dealing with a slightly more difficult integral if it means it is easier for you to get through the setup. The setup is generally the hard part. And so if that's easier in cylindrical, it might be worth a trade-off of having some non-constant limits of integration, which will happen in cylindrical but not in spherical, as we'll see. So let's do it in cylindrical, we'll do it in spherical as well, and you're welcome to use either method here. Sometimes I may specify which coordinate system I want you to work in, but if I have not specified, then you're free to use whatever seems best. Here's our region. It still looks like it did before. We are definitely going to represent cylindrical as polar plus z, because it is the xy plane that has this nice circular projection, or it's rather a disk. The projection of our region to the xy plane is a disk, and so we want to represent that xy plane in polar. So we're going to work with cylindrical being polar plus z. In the what is now the r theta plane, I'm looking at the unit disk centered at the origin, and that's one of the simplest regions to describe in polar coordinates. We'll have theta going from 0 to 2 pi, we have full circular symmetry, and r is going from r equal to 0, which gives us the origin, through all radial values until you reach r equal to 1, which is the outer edge, the outer boundary of this region. And z in rectangular looked like the square root of x squared plus y squared less than or equal to z, less than or equal to this expression for the upper half of the sphere. If we translate that into cylindrical, it does simplify a bit. So now we're looking at r less than or equal to z, less than or equal to the square root of 2 minus r squared. And that's not as nice as something could be. There's still a square root involved, for instance, here. Though it is considerably nicer. The left-hand boundary especially, or the lower boundary from z, simplified considerably. And now we can describe E in cylindrical as theta going from 0 to 2 pi, r going from 0 to 1, and z going from r to the square root of 2 minus r squared, the positive root of 2 minus r squared. So if we set up our volume of this region as an iterated integral in cylindrical, it will take this form. Theta is going from 0 to 2 pi, r is going from 0 to 1, and z is going from r to this square root expression. We also introduce an extra factor of r into our integrand that is introduced, or that is part of the dv expression in cylindrical. So that comes into play when we rewrite dv as r dz dr d theta. So I'm integrating first with respect to z. I'm going to have r times z. I'll plug in my upper and lower limits of integration for my z variable. And here's r times the upper limit of integration for z. And here's r times the lower limit of integration for z, r times r. Now at this point, I have an integrand which can be factored as a function of r, the whole of this difference, times a function just of theta, which is 1. And I've got constant limits of integration, so I can factor this double integral out into two single integrals. The integral with respect to r, I'm going to break up into two integrals with respect to r. So I've got the integral with respect to r of this difference. I write it as the difference of the two integrals. I do that because one of them here is simple. It's a polynomial. I can integrate that straight away. I get 1/3 r cubed, 0 to 1. The other involves a u substitution. So I wanted to separate the two integrals so I could apply the u substitution to just this expression. My u factor here is going to be 2 minus r squared. I've got my du expression. This integral simplifies in this way. And then I can take an antiderivative of the square root of u and end up with u to the 3/2. That is a 3 over 2 there. My coefficients are changing as things cancel out. And I will resubstitute from u back to r before plugging in my 0 and 1 for my r values there. The other integral with respect to r, as we said, is relatively simple. I plug in the limits of integration and get minus 1/3 here. And the integral with respect to theta was particularly simple. We just pick up a factor of 2 pi. This expression now simplifies. You got to do a bit of algebra here, but the final answer is 4/3 pi times root 2 minus 1. So this is the volume, and it is a positive quantity because the square root of 2 is greater than 1, so everything's positive here. This is the volume of that ice cream cone found in cylindrical. We set it up in Cartesian. Had we been able to solve, this would have been the answer we got. The answer does not change based on the coordinate system. We're just talking about the volume of a geometric object. The object doesn't care how we describe it. It simply has a volume. So had we been able to compute the integral in Cartesian, we could give this answer. In fact, we know that this is now equal to that triple integral that we set up in Cartesian, though we actually found it by solving the integral, or solving for the volume in cylindrical. Let's do it in spherical. we should get this same number. So here's the answer we got in cylindrical. If we approach the problem in spherical, it would have to come out to be numerically the same, as it's just supposed to be the volume of an object. So let's attempt this. What is it going to look like? We will have, in spherical, I gave you some hints when we talked about spherical in last lecture, that for spherical, the tricky part for a lot of folks is thinking about the two angle variables. And so when you're thinking about theta, try to project your region into the xy plane, and that'll help you to think about just how theta works. And when you're thinking about phi, try to project your region into the xz plane to sort of isolate where the phi variable lives, and think about that angle. Here we have theta going from 0 to 2 pi because our projection into the xy plane has full circular symmetry. In the xz plane, we have, with y set equal to 0, our equation for the cone becomes z equal to the square root of x squared, and that corresponds to z equal to x and z equal to negative x, those two straight lines. Both of them do lie on the 45. Z equal to x has slope 1, so over 1 up 1. And that means that this angle phi for this outer portion of the region is just going to be given by phi equal to pi over 4. Phi equal to 0 is the z-axis, phi equal to pi over 2 is the positive x-axis, z equal to pi over 4 is giving me this region on the 45, this line on the 45-degree angle. So phi is going from phi equal to 0, where we have, you could imagine taking a pencil, setting the eraser at the origin, standing the pencil straight up, that's phi equal to 0. We then let it swing down until we hit phi equal to pi over 4. And that gives us all the values here in this range of values for phi. And once again, remember that the other side, that actually comes from the theta value. When you rotate about the z-axis, we just have to worry about z going from a positive value, or from 0 down to some positive value here. So phi is going between 0 and pi over 4 to describe this region. And finally, rho is going from rho equal to 0, which is the origin, out to rho equal to the square root of 2, which is the radius of this upper portion of the sphere. So even if I follow along one of these outer edges here, I would be going from rho equal to 0 to rho equal root 2. If I go straight up, I go from rho equal to 0 to rho equal to root 2. If I come out this way, I'm going from rho equal to 0 to rho equal to root 2. So that, going from the origin out to the sphere, which forms our ice cream top, that is taking rho from 0 to root 2 for all values of theta and for all values of phi. That's what we want. So in fact, this region, this is now how you describe the region. These are the bounds for all three of the variables. And this region is a rectangular box in spherical coordinates. We've got constant bounds for each of our three variables, which makes it a rectangular box in spherical coordinates. So we can now compute the volume of this region as an iterated integral in spherical coordinates. The volume of E is always the integral of 1 over E. The triple integral of 1 over E. Written as an iterated integral in spherical, we've got rho going from 0 to root 2, theta going from 0 to 2 pi, and phi going from 0 to pi over 4. I introduced the factor of rho squared sine of phi by moving into spherical coordinates here. Everything here, all my limits of integration are constant. My integrand factors nicely as three functions, each of which depends only on one of the variables. My function with respect to phi is sine of phi. With respect to theta, I have constant function 1, and for the variable rho, I have the function rho squared. So I can factor my triple iterated integral into the product of three single integrals, and I can compute each of those. So the antiderivative of sine is negative cosine, the antiderivative of 1 is theta, and I get 2 pi as I take that from 0 to 2 pi, and the integral of rho squared is the third rho cubed. Plug in my limits of integration and do a little bit of algebraic simplification, and we again get our 4 pi over 3 root 2 minus 1 expression. So it was the same for cylindrical and for spherical. We would have gotten the same answer for Cartesian had we been able to actually compute it. So let's do some more of these. Here's another sample problem. Here is a triple integral. I throw it to you just like this, and I ask you to solve it. Give it some thought. All right. So this problem looks bad, and this is the kind of problem that's designed to freak people out when they first view it. But it's not actually that bad. It's only bad if you attempt to remain in Cartesian coordinates like we are now. But that would be foolish of you. You do not want to remain in Cartesian coordinates. Instead, you want to think about what the limits of integration tell us about the region, reconstruct the geometry of the region we're being asked to integrate over, and then decide to re-express that region using a different coordinate system. So we're going to walk through and think about what is happening. I don't like this initially. I look at this integral and I think, no way is that the way it's supposed to be. Like, that doesn't look natural. I want to do something different. I think a new coordinate system is going to be most appropriate. So I'm going to spend some time trying to reconstruct the region that we're being asked to integrate over from the limits of integration that we've been handed. And then I can decide, based on the geometry of that region, which coordinate system would be most appropriate to approach the problem in. So let me swing back up here a second. I've got x going from -2 to 2. That's the easy part. Y is then going from some function of x to some other function of x. That's relatively easy. And then finally we'll think about what's happening with my z variables here as they move from one surface to the other. So what is this region? We said x was going from -2 to 2. Those are the limits of integration for x. That's just giving me an interval of length 4 centered at the origin. That's easy enough. Then my limits of integration for y were the negative root of 4 minus x squared and the positive root of 4 minus x squared. Y equal to negative 4 minus x squared, hopefully you can at this point recognize that that's the lower half of a circle of radius 2 centered at the origin. If I take an equality here, I take these two things to be equal and I square both sides, I would get an equation for the circle of radius 2 centered at the origin. And in fact, because I'm looking at the negative root, I am only taking negative y values. If y is equal to this expression, then y is always negative. And so we're looking at the lower half of this circle. And then y equal to the positive root is of course going to give me the upper half of the same circle. So x is sliding from -2 to 2. For each of those x values, y is going from the lower curve to the upper curve. At this point, we can see that in the xy plane, the projection of our region is a disk of radius 2, centered at the origin in the xy plane. Finally, let's think about what z is doing. And just like what we did a moment ago, z is going from the lower half of a sphere of radius 2 centered at the origin to the upper half of a sphere of radius 2 centered at the origin. So our shaded disk is now just the sort of midpoint cross section. And we're going from the lower hemisphere to the upper hemisphere here for all of our z values. And so this region that our limits of integration describe is actually the ball of radius 2 centered at the origin. And a region could not be simpler to describe in spherical coordinates. We're going to let rho go from 0 to 2. We're going to let theta go from 0 to 2 pi as we have full circular symmetry in the xy plane. And we're going to let phi go from 0 to pi. So theta and phi are both getting their full range of values, and we're taking radii from 0 out to 2 to get all of those concentric spheres that together give me the ball of radius 2. So the integral that we were asked to compute and looked so bad becomes simpler. So my limits of integration are all becoming much simpler. This is a d rho, d theta, d phi integral, and here's my limits for rho, my limits for theta, and my limits for phi. And my integrand actually simplifies in some ways as well. The x squared plus y squared plus z squared expression is just going to become rho squared. And then we've got the 3/2 power on top of that. And then my dz dy dx is going to become rho squared sine of phi, d phi, d theta. I'm sorry, d rho, d theta, d phi. So the existing integrand did simplify a little bit, but we also introduced a couple of new factors into our integrand by switching to spherical coordinates. In fact, we're going to end up with the integral from 0 to pi of sine of phi. We'll have the integral of 1 from 0 to 2 pi, and we will have the integral of rho squared e to the rho cubed from 0 to 2. So actually, the rho squared expression that we introduced by switching to spherical is going to be a benefit here. This is going to allow us to perform a u substitution and actually solve this integral with respect to rho. If you integrate sine from 0 to pi, you get 2. If you integrate 1 from 0 to 2 pi, you get 2 pi. And the antiderivative of this expression looks like this. So 1/3 e to the rho cubed You can double check me. If you differentiate this, the chain rule should bring you back to rho squared e to the rho phi. I'm glossing over a minor u substitution for this portion. But then rho is going from 0 to 2. I can plug in values and I end up with 4 pi over 3 e to the 8 minus 1. There's another 4 pi over 3 factor showing up just like it did in the last example. That's purely coincidental. This is a different value, and this isn't even a volume that we're computing, but rather we were just finding this integral. So the integral of this expression over the unit ball of radius 2. So I threw the problem at you in Cartesian. It was terrible looking. You could use the limits of integration that were given in Cartesian to reconstruct the geometry of the region that you're integrating over, and based on that geometry we decided to approach the problem in spherical instead. The region was the ball of radius 2, right? 2? Yes, the ball of radius 2. So by approaching the problem in spherical instead of in Cartesian, we turned a hard problem into an easy problem. And that is the daily work of math folk. Turning hard problems into easy problems. Alright, so let's have you do another one of these. Here's a problem. Here's a iterated integral in Cartesian coordinates that I would like for you to solve. Alright, that should have been plenty of time to pause the video. Let's consider a solution. Doesn't look natural to me. Doesn't look great. Backing up real quick. I see a bunch of limits of integration. Here's a circle for x, so something's up with that. And I know expressions of this type would simplify were I to move into cylindrical, for instance, so maybe that's going to be of interest to us. It doesn't look terribly natural to me. I want to think about what the region looks like. So based on my limits of integration, we had y going from -3 to 3. We had x going from, and I can draw that interval for y. Y is on the vertical axis from -3 to 3. For each of those y values, we had x going from a left-hand curve to a right-hand curve. X equal to this negative square root is going to give me the left half of a circle of radius 3 centered at the origin, and x equal to this right-hand expression is going to give me the positive, or the right-hand half of such a circle. So I've drawn those pictures here. X is going left to right for all the values of y. Y is a little bead on a string sliding from low to high, and for each associated y value we have x going from left to right here. So in the xy plane, we're looking at a disk centered at the origin of radius 3. In the z direction, we had the square root of x squared plus y squared less than or equal to z less than or equal to 3. Z equal to this square root expression we've talked about earlier today. That's given me the cone, the upper half of the right circular cone, centered, or with its apex at the origin rather. And z equal to 3 is just a horizontal plane, parallel to the xy plane, but at height 3. So this is just the cone, effectively. We no longer have our rounded ice cream top. We just have a cone, and it's lopped off at the height 3 here. So we've got sort of the tip of this cone, or this half cone, rather. So that's what that looks like, and I like cylindrical here. Spherical worked well when we had that spherical top, but spherical is not going to work so well for this. Cylindrical is going to be much more appropriate. If I try to do this in spherical, rho gets to grow larger from, rho's going from 0 out to a larger number along the edges of the cone, but rho is going from 0 to a shorter number dead center in the cone. So when phi is 0, my rho value is smaller than when phi is at pi over 4, for instance. And so it's not going to be as nice. It's not going to be appropriate to try to describe this in spherical rather. Cylindrical is going to be best. In cylindrical, we had the disk of radius 3 in the xy plane. That's going to let theta go from 0 to 2 pi and r go from 0 to 3. And then our bounds for z become simply r less than or equal to z less than or equal to 3. So it's not a rectangular box in cylindrical. We have this one non-constant bound. But it's pretty nice. Every other bound is a constant, and it's expressed easily and neatly. So the triple integral we were asked to find is actually going to be equal to, we're going to write this as an integral in cylindrical, where cylindrical is polar plus a z. Theta is going from 0 to 2 pi. R is going from 0 to 3. Z is going from r up to 3. We introduce an extra factor of r. Z is still z, going from Cartesian to cylindrical, but x becomes r cosine theta. So this is how the integral translates. We are able to translate our integrand and our dv expression just based on our equations for translating between Cartesian and cylindrical, and also our knowledge of what dv looks like in cylindrical to get this extra factor of r. But to change the limits of integration, we had to go from the old limits to the geometry, and from the geometry to the new limits. And now we can perform the integration. So there's nothing terribly surprising here. We integrate with respect to z first, and z becomes 1/2 z squared. We plug in some values. We can simplify things a bit. In fact, we can factor the cosine theta out. So we have a function just of theta and a function just of r. We can, now that the only non-constant limit of integration has been dealt with, all of our remaining limits are constants, and we're able to factor our integral, our iterated double integral, into two single integrals multiplied together. One of them is 0, so the whole thing is 0. We don't actually have to mess with the other one. As soon as we see that cosine theta taken from 0 to 2 pi is 0, then we're done. Alright, and we will wrap the first part of today's lecture there. That was a lot of pages, so I'll get this posted and I will begin working on the second part of today's lecture. It looks like it might go up a little bit late, my apologies for that, but we'll get it up today and we'll get another lecture up later this evening so that we're all caught up. I thank you folks, more practice incoming.